Our next topic in geometry is similar triangles and similar figures. If we have figures that are the same shape, but they're not necessarily the same size, they're called similar. These two fellows are considered similar. Now they're not the same size, they don't have to be the same size, but they are the same shape. The one on the right is an enlargement of the one on the left. These two guys are not similar. The one on the right is larger than the one on the left, but proportionally he's a lot wider than the one on the left is. How about these two shapes? Do they look similar? Well, they are. The one on the right is an enlargement of the one on the left. How about these two? They're not similar. The one on the right has been stretched taller than the one on the left, but proportionally, the one on the right is not proportionally larger than the one on the left. If we have polygons, they're similar if corresponding angles are congruent and the lengths of the corresponding sides are proportional. So if we look at the rectangle that we saw before, and we say that this rectangle measures 3 centimeters by 5 centimeters, and we look at a larger rectangle that measures 6 centimeters by 10 centimeters, these two figures are proportional and the angles are congruent, so they would be similar. Now by proportional, what we mean is that the lengths of the sides of the one figure are some multiple of the lengths of the sides of the other figure. So in this case, 6 is 2 times 3 and 10 is 2 times 5. So the dimensions have been doubled to get the larger rectangle. How about two squares? Do you think that they're similar? Well, all squares are similar because all squares have congruent angles. They all have right angles, and the lengths of their corresponding sides are always going to be proportional. How about two equilateral triangles? Are they similar? Well, yes, they are. Equilateral triangles will always be similar. They have 60-degree angles, and the lengths of their sides are proportional. How about these two right triangles? Are they similar? Well, they're not. If you look at the two triangles, the one is stretched taller than the other one. The one on the right is actually pulled longer in the vertical direction than it was in the horizontal direction. So these two are not similar. Now when it comes to similar triangles, we can look at a theorem that can be used to show that two triangles are similar. And that theorem is called the angle-angle-angle theorem, which says that if 3 angles of one triangle are congruent to 3 angles of another triangle, then the triangles have to be similar. So take a look at these two triangles. Let's say that angle A and angle D are congruent, and angle B and E are congruent, and angle C and F are congruent. By the angle-angle-angle theorem, triangle ABC is similar to triangle DEF. And you'll notice the notation that we're using to show that two triangles are similar. It's that tilde symbol. The other thing you need to notice is that the order that the letters are given to us in the names of the triangle are implying some things about these two triangles that are similar. So if triangle ABC is similar to triangle DEF, then we know that angle A and angle D are congruent triangles. That's because those two angles are mentioned first in the names of each of the similar triangles. Angles B and E must be congruent because those angles are mentioned second. And angle C and angle F must be congruent because those angles are mentioned third. Now we also know something about the side lengths of the two triangles. We know that the side lengths are proportional, and that would be the corresponding side lengths. So in this case, side AB and side DE are proportional to each other. Side BC and side EF are also proportional to each other, and sides AC and DF are proportional to each other. So since we know we have similar triangles, let's suppose that we also know something about the lengths of their sides. So since side AB and side DE are proportional, that means we can form a fraction from those side lengths and have the fraction 9/15. Side BC and side EF are proportional, so we can form a fraction out of their side lengths. And side AC and side DF are proportional. So because these two triangles are similar, these three fractions that we've just formed have to be equal to each other. So let's look at a proof that involves similarity. We want to prove that triangle ACB is similar to triangle ECD. Now keep in mind that what will make two triangles similar is if we can show that we have three pairs of congruent angles. So let's start as usual with something that was given to us in the proof. And we were given that angle A and angle E are congruent because those angles are both marked as right angles. We know that angle ACB and angle ECD are congruent because they're vertical angles. And we know that the measures of all the angles in the triangle on the left have to sum to 180 because all the angles in a triangle sum to 180. Now the same holds true for the triangle on the right. All of its angles must sum to 180. So if we combine the three statements that we've just written, we can conclude that angle D and angle B have to be congruent, and that's using some algebraic substitution. And finally, we can say that the two triangles must be similar because we have already stated that three pairs of angles are congruent in the triangles, so by angle, 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 the triangles must be similar. So we've proven that these two triangles are similar. Let's suppose that we know some of these side lengths. Suppose we know that side ED measures 5 units, and side CD measures 7, and side AB measures 8. How can we use those measurements to find the length of side BC? Well, we need to set up some proportions to show which sides are proportional to each other, which sides form those equal ratios. So BC, which is the side we're looking for, is a corresponding side to side DC. One thing to look for in the picture is that in both triangles, those sides are opposite the right angles. And that side AB and side ED are also proportional to each other because they are opposite congruent angles. The congruent angles being the vertical angles that you see that contain point C in the middle of the picture. So we can substitute some numbers here. We know that DC measures 7, that AB measures 8, and that ED measures 5. So now that we have a proportion, we can cross multiply to solve the proportion, and finally have the measure of side BC as 56/5. So here's another picture that has some similar triangles in it. Now it may be a little hard to see the similar triangles, so we're going to end up pulling this picture apart a little bit. And once we do that, we're going to take these lengths of the segments that we've been given and put them into the picture. So the similar triangles are the smaller triangle that you see on the top of the picture, and then the larger triangle that contains that smaller triangle. We would like to find the measure of segment AD and the measure of segment DE. So here's the two triangles that we need to look at as similar triangles. The large triangle is triangle ADE, and the smaller triangle is triangle ABC. We've been given the length of AB as 4, and we've been given the length of BC as 5. We've also been given the length of AC as 6. So in the small triangle, we know the lengths of all three sides. Now in the large triangle, we haven't been given the lengths of any of the sides directly, but indirectly we have been given the length of one side. And that's because we were told that the length of CE is 2. We also know that the length of AC is 6, and those two lengths together make up the length of AE, which is 8. So let's say we'd like to find the length of side AD. We need to set up some proportions to show some fractions which represent those corresponding sides. So the side that is labeled as X units long, which would be segment AD, is opposite the angle that's marked with one tick mark in the large triangle. And the side that's opposite that same angle measure in the small triangle is the one that measures 6. So X and 6 are proportional. In the large triangle, the side that measures 8 corresponds to the side that measures 4 in the small triangle. Now if we cross multiply and solve, we've got the length of side AD, which we called X. Now to find the length of side DE, let's give it a name as well. Let's call it Y, and let's set up a proportion to show the side lengths that are corresponding to each other. So in the large triangle, the side that measures Y units long is opposite angle A, as is the side that measures 5 units in the smaller triangle. And that corresponds to the side that measures 8 units in the large triangle and the side that measures 4 units in the small triangle. If we cross multiply and solve, we'll get that Y equals 10, which means the measure of side DE is 10 units long. So let's look at one last problem that uses similar triangles. Allie is 4 feet tall and her shadow is 6 feet long. A nearby flagpole has a 36-foot long shadow. How tall is the flagpole? Well, let's draw some pictures to see what's going on. There's the sun, there's Allie. She's 4 feet tall and her shadow is 6 feet long. There's a flagpole nearby that has a 36-foot long shadow. we want to know how tall the flagpole is. So we'll call that x. Now let's say we look at some triangles that are formed in these pictures and try to find the sides that are proportional in these similar triangles. Well, certainly the x and the 4 are proportional, as are the 36 and the 6. So let's write a proportion that states that, and then cross multiply to solve. And we find that x is 24. So the flagpole is 24 feet tall. So remember, similar triangles have congruent angles and proportional sides. The angle-angle-angle theorem is used to show similarity. It's not used to show that two triangles are congruent. That's what our other triangle congruence theorems are for.